Part 1. As you can see, there is a part 2 to the practical part. Well, first some general steps before we actually do it, of course. The general practical steps in doing hypothesis tests in real-life situations is, the first, in a way we need to be pretty clear about what the hypotheses are that we are looking at. And what is the risk level, the alpha risk level, the type 1 risk level of wrongly claiming something. This is something we have to specify, something very often that is given to us by the settings. Often alpha is 5%. I mean, the most used alpha is 5%. Then we look at data. We measure, of course, the difference between the actual data that we have and the claim which is given. It's not so complicated, actually. There is a claim, we have some data. What's the difference? That's looking at data. We transform this difference into a probability because it can be difficult to evaluate whether such a difference, are we far away from the claim or are we close to the claim? Well, that depends on the noise and the variability and the probabilities in the system. So we transform this difference between data and hypothesis into a probability. And we use this probability to make a decision. That's the fourth part. Right? Hypotheses, look at data, transform this looking at data into a probability, the p-value, making a decision based on the size of this p-value. That's hypothesis test. Slightly more specific, before it becomes very specific. We go to the general treatment of hypothesis test for a mean. That is what we're going to be taught today. Then later in the course and out there in future courses and in the rest of your lives, there are hypothesis tests related to many other computations and claims about different things that you could make. Today it's just the mean. So let us make the classical assumption that either the data already comes from a normal distribution in the beginning, or we have large enough information, that is at least 30 data points in our data set, such that we can ignore whatever due to the central limit theorem, such that we can work with the normal distribution as our probability tool in doing such things like we did with the confidence interval. We test a hypothesis like this about the mean. Here it comes. I didn't say we can have an alternative. The alternative can be two-sided or one-sided. Here's the test statistics, and I hope it looks slightly familiar to you. Actually, we are still running around in the same numbers as we've done the last couple of weeks. Don't you think that it sounds a bit obvious that we should take the data and compare explicitly with the hypothesis, with the claim? I think that makes good sense. I even said it a few times already. We should, of course, see how far away from the hypothesis of the claim is the data. Then, the way we should be intelligent, even more intelligent, is to realize that this x bar has a variability and a distribution, as I said previously today. Using this distribution, we have such a standardized measure here. It's a standardized measure of a difference between the claim and the data, between the hypothesis, the null hypothesis, and the data. Then we transform this value into a p-value. And this is maybe the challenging part. Having done that, I'm going to show you in the example how we do it. Let's just, you have a feeling of that we can do it. Then we make a decision. Finally, we transform the computed set into a probability, that is the p-value. If this p-value is too small, or rather small enough, and that is smaller than the decided risk level alpha, then we reject the hypothesis. That's the first part. If this p-value is not or rather larger than alpha, we accept the hypothesis. Let's try to do it, and then we'll think about the interpretations of this while we're doing it. So this is the same story as before, and here comes some numbers for that example. Remember that we were assuming, let me just make sure, yeah, we assume the variance is like this. So for now we don't compute the variance, we'll do that later. Now we assume this. If we have 12 computer screens tested, we see that the average came out like this. Actually, again, I should here, when I use it for the actual number, use small x bar. Carry out the hypothesis test. Actually, why not use the most commonly used level of 5% the first time we do it? 5% is the most commonly used level. So let's use that. How should we do it now? The null hypothesis, let me rephrase that, is that mu equals 83. The alternative is that mu is larger than 83. Now, we should compute the test statistic. 2 slides back, 3 slides back, I had the test statistic, which was the observed average minus the claimed level, right? I think that makes good sense that these are the numbers we should compare, right? What comes out of the data? What do the company claim? Of course, we should look at this number, I would say. I think most people would have done that also back in elementary school, at least looking at this difference. Then, of course, making a judgment based on this difference is harder. Because what could we expect from such a difference? That is difficult to know in elementary school and in high school. For knowing what we could expect of such a difference, to realize whether when we see something that is larger, is that really proof enough of something is wrong here? Or is it just an acceptable sort of feature of the variability of the system? Very difficult to judge by heart or just by looking at the numbers. Here we have to be intelligent. We have to root 12. Do we agree that this is the number that comes out of the test statistic shown you before? We make a standardized difference between the data and the hypothesis. Let me do it. And R. Whoop, sorry. Can you see this? I'm taking the difference, the 1.92, that was the difference between 84.92 and 83, right? I divide by 4 over root 12. What do I get? I get 1.66, right? 1.66. 1.66 is a measure of the difference between the data and the hypothesis. Now, if there is a large difference between the data and the hypothesis, that should lead us to a rejection of the null hypothesis, right? I mean, if the data is far away, we should reject the claim. If the data is close to the hypothesis, we should accept the claim, right? Can you follow this? I believe this is common sense, right? If the data looks like what they claim, we have to accept it. If the data is far away, we should reject it. That's the core of it. Defining far away can sometimes be challenging in the sense that here we need to think about whether far away is a one-sided thing or a two-sided thing, actually. We have to take that into account in our thinking of what is actually far away from the hypothesis. In this case, it's a one-sided situation. So I will claim that, also following my thinking in my stones and my sand last time, it's the same kind of thinking, that here I have somewhere, I have 1.66 in my standard normal distribution. I would claim that, and not only me, but also the theory claims, that the relevant p-value is to try to find out how odd is my actual outcome in the light of the hypothesis. Is it likely to hit 1.66, or is it unlikely, right? That's the key. Is it, am I unlikely far away, or am I likely close to the claim, right? Is it unlikely, or is it likely to go this far away? If it's very unlikely, if I'm far away, it becomes unlikely and I reject. I'm repeating the line of thinking here again and again. So I need to find this likeliness, this probability, this p-value as we call it. The p-value in this case is the probability that a standard normal exceeds 1.66. Because I would say that if I'm going to judge whether 1.66 is odd or unlikely large, I would say let me find 1.66 and everything above it. That is the most reasonable thing to do. I mean, 1.66 on its own has no probability. That's just a point on a continuum. I think that the relevant probability would be to find this one. Hope you can follow me or can learn to follow me. If you can learn to follow me sometimes before the end of the course, you're doing well. So don't panic if you have difficulties now. What is the probability of getting this? This is something I can find either in table 3, this is the standard normal in this case, or I can go into R and find it here. What is the probability of going beyond 1.66? This probability is 4.8%, 0.048. Seeing a difference of 84.92, seeing such a larger average level of this, would only happen in 4.8% of all cases if the company is true. I mean, if we give the benefit to the company and saying, if what they claim is true, then such a deviation as 1.84.92, which transformed to a standardized scales, becomes 1.66. Such a deviation only occurs in 4.8% of all cases. Then we make the decision now, because we compare this p-value, that's the last step of the level 1 of the practical hypothesis test. Step 1 is, since this is smaller than alpha, and we used alpha here, 5%, because we observe that the computed p-value probability is smaller than the specified 5% alpha, then we make the decision of rejection. We have seen something that is unlikely if we put alpha, 5%, as the level of unlikeliness. So we claim that they are not right in their claim. We say that we have proved with the numerical evidence that they are wrong. And if both me and the court of law accepts the risk level of 5%, I have a case here. Of course, with another risk level, the conclusion could have come out differently. But if we both accept, that's the thing about risk levels, both the sender and the receiver, that's something you have to agree about when you do something. Can we agree on the risk level before we do it? If we agree on the risk level, then we make a decision. In this case, the decision is reject the claim. There is something wrong in your specification of those computer screens. Right? That's hypothesis test. We need a break. 15 minutes.